Okay, hello everyone. I'm very happy to welcome Çağlar Aytekin, a graduate of our department who has been very successful in academia and industry. He's visiting us from Finland today. Çağlar received his bachelor's and master's degrees from our department in 2008 and 2011. He received his Ph.D. from the University of Tampere, Signal Processing Department in 2016. Until 2019, he worked in Nokia as a senior scientist. In 2019, he joined AAC Technologies, where he is currently working as AI team leader. He has over 40 publications and around 30 patents. He won ICPR 2014, which I believe is a very significant feat, an IBM Best Paper Award, and 3 Best PhD Thesis Awards separately given by the City of Tampere, University of Tampere, and Scandinavian Conference on Image Analysis Council. His research and business interests include deep learning and application of deep learning in imaging, computer vision, and pattern recognition. So we're very excited to hear what Çağlar has to say to us today. Thanks again.
All right, thank you very much for the introduction. So let me share my screen. Okay, thank you very much once again for having me. I hope you can see the presentation. Okay, all right. So yeah, today I'm going to talk about what I'm doing in my current company, basically transforming the mobile imaging industry with deep learning. I intentionally selected the title a little bit bold, but I still believe that's what we are doing here. So, and outline of my presentation is as follows. First of all, I'm going to talk a little bit about deep learning and not doing, of course, too many details. And then I'm going to discuss what is and why is image signal processing pipe is needed. And I will also further talk about mobile imaging, what is the differentiating factors of mobile imaging from normal, like high-end DSLRs, for example. And then, of course, I will combine these two topics and discuss opportunities of applying deep learning in mobile imaging and related challenges. And hopefully by a case study, I will give an example how we apply deep learning to a specific mobile imaging problem, a specific block in ISP pipe, which is image denoising. And later on, just the one slide, I will talk briefly about the other stuff that we are doing in AAC Technologies.
So if I may just interrupt you, you may want to share your full screen presentation view.
All right. I think that's the, just a second. How about this one? Is it better? Okay, yeah. So for those of you who have some background in deep learning, I'm sure this visual in the slide is, you have seen this, I don't know how many times, but I just still wanted to put it. And the difference between the deep learning and the traditional way of doing things in machine learning prior to deep learning is basically the end-to-end paradigm that is introduced by deep learning. Prior to deep learning, the classical way of, for example, doing image classification was to rely on some handcrafted, human-designed image features and also some descriptors of those features, and then basically give them to a classifier and do the task. However, the bottleneck here is the human element. So basically, we are limited by our assumptions of the feature descriptors and feature detectors. The deep learning, what it introduced is it also automized this feature extraction and description part and introduced an end-to-end paradigm. So basically, you only give your input and the desired output, and the deep neural network learns whatever in between. So there are minimal human intervention. Of course, there is a neural architecture design element that is still partially done by humans, but I will come to that. By definition, any neural network that has larger than 2 layers are considered to be deep, 2 hidden layers. And as I said, the advantages over traditional machine learning is basically the end-to-end paradigm, universality. So there's a theorem that says, like, given enough depth and width, these deep neural structures are able to arbitrarily approximate any differentiable function. And deep learning takes advantage of a large number of data samples, much better than the other methods. So usually the other methods gets saturated after some point of data, the data set, but deep learning's performance usually increases more and more as your data set grows, and it is able to solve really complex problems. And throughout the history, there have been many breakthroughs for deep learning, and I think like most of the breakthroughs come from how to train these neural networks and solve some problems in training these very complex structures. And like, first of all, the backpropagation itself is still the dominant technique to train the neural networks. Although it is very simple, it's just updating the weights in the negative direction of the gradient. It needed to be introduced to train these networks. And then again, in order to let the gradient flow smoothly to the earlier layer so that you can basically train deeper neural networks, rectified linear units were introduced over sigmoid, and skip connections in residual neural networks. And a part of the trainability, there were some other breakthroughs. For example, I think all of you have seen one way or another these AI-generated images or videos in the internet that looks very realistic. And generative adversarial networks is the technology behind that. And more recently, like as I said previously, there is still a human element left in deep learning, which is the neural architecture, and like there have been some automation efforts in searching that for that architecture using a controller as well. So I had an observation that deep learning had its very fast and hard impact on the problems, on a family of problems. It came first to the classification, detection, segmentation like problems. And like one intersection of these problems is that the fact that they cannot actually be formulated very well as a mathematical equation. So because of this fact, actually you have to rely on many assumptions in order to produce handcrafted solutions to these problems. However, the impact of deep learning came and is coming a little bit later to some other problems that you can more or less accurately formulate. For example, if you talk about super resolution problem, the downscaled image is nothing but a convolution with a blur kernel and then downsampling operation. So whenever you have some sort of formula, then you can invent a more or less accurate way of solving this problem. But as I said, deep learning impact came a little bit late to this area. However, now it's starting to dominate over the classical methods in this area as well. And today, the most of the problems that I'm going to talk about and we deal in AAC are related to this second family. Having said that, let's talk a little bit about image signal processing pipe, and because the problems here are just the ones that I have just talked about. Most of these problems are actually coming from the physical image acquisition system. So let's review that very fast. So basically everything starts with light hitting the subject, and then it goes through a lens and this lens introduces its own errors like lens shading, and then there's this blurring, and after that it hits the mosaic filter where basically in every pixel there is a bandpass filter. It just transforms, passes through some band of wavelengths. So there is an information loss there. It's another type of loss in the system. And then later on, there's this image sensor, which introduces a sort of complex noise into the image. And then finally, there's an analog to digital converter, which introduces its own noise, read and quantization noise. And then we end up with either 12-bit or 16-bit, usually, raw image. So the job of image signal processing pipe is first to recover these losses that I've just talked about coming from the physical acquisition system, and then later on try to match the colors of the perceived scene to human visual system. And of course, there are a few more steps to come up with a more perceptually better image. Mobile cameras, on the other hand, have their own limitations. Moreover, to this physical acquisition systems, for example, the size of the lenses that we use in mobile phones are like insanely smaller than the ones we use in high-end DSLRs. And in high-end DSLRs, usually the lens is glass, and in mobile phones, it's usually plastic. Not usually, but almost always plastic. And in order to simulate the effect of a one big glass lens, we have to use 6 or 7 very tiny plastic lenses, and which introduces even more errors. However, we need although we need a much better ISP to recover these even more losses, that is also very difficult because the computation for doing the ISP is limited in mobile phones too. So it's actually a very difficult problem. So how can we actually apply deep learning in mobile imaging? Like, first of all, as I said, since we need very, very powerful algorithms in order to solve this inverse problem, we kind of need a strong enabler like deep learning models. So it basically has applications in basically all of the blocks that we have in ISP. However, it comes with its own challenges. Like first challenge maybe is, as I said, the computational limit that we have in mobile phones, and it's basically related to the limit of the neural processing units or graphical processing units in the chipset. And data sets, it's a problem on its own, because in most of the problems in ISP, we basically do not have a ground truth. So, okay, you capture an image and you have a noisy image, but what is the ground truth? Like, it's not as easy or like as straightforward as, for example, having a ground truth in image classification where you can always label your data later on. I'm not saying it's easy, but it's at least there is a ground truth extraction process. So we need to invent some ways to have the ground truth. And another difficulty to apply deep learning in imaging is the dependency of the algorithm to either the camera module or the characterization. Well, actually, you can maybe generalize by just saying characterization. For example, if you train your neural network for a handful of cameras, and whenever you have a new camera, then the noise characterization, for example, if you're doing denoising, will change a lot. And then you will either need to collect some data set and retrain your neural network, and it becomes infeasible after some point. So we need to solve these challenges, basically. So let me try to explain our solutions to some of these challenges in a case study, which is image denoising. So we intentionally selected image denoising as our first AI project, since it is usually the first block in ISP. And basically, image denoising quality determines the rest of the the success of the rest of the blocks. So if you cannot really get rid of the noise in the first stage, then every other block that comes on top of it will basically accumulate that error. So this is arguably still the single most, in my opinion, important block. So let's start maybe with the sandstorm noise model. So the photons hit the surface, and then there's this quantum efficiency multiplier, and that there is a noise here, which is the photon counting noise, and it's usually represented by a Poisson distribution. And there's also other type of noises in this acquisition system, like dark noise, which is usually related to the temperature of CCD. And then there's another analog gain in order to amplify the signal, which is just another linear multiplier. And later on, we have to, of course, convert this analog signal to digital signal, and there's another noise coming from there too. So these two noises, the dark noise and the read and quantization noise, usually are approximated by Gaussian distribution. So in ideal noise-free case, it's just multiplication with two numbers here, but as we know, it's not the case, and we end up with some formulation like this, where X star is basically the image that we are after, and X is the image that we have. So existing algorithms, of course, there have been decades of research in image denoising, and one obvious thing that one might think is, why not take many images of the same scene over time and average them, because like then you reduce the variance and your estimated expected signal is the ground truth itself. However, it comes with its own challenges. For example, you need to have a very static scene and very static camera in order to be able to do time averaging, which usually we don't have. Like even some micro moments in your hand will distort the image a lot, and then you will now have to deal with image registration, although there are still multi-frame approaches. I think the most dominating classical approach to denoising is the self-similarity. So instead of averaging over the same pixel over time, why not average intensity values of similar pixels over the image? So there have been a lot of work on this, like non-local means, bilateral filtering, etc. And CNN-based methods, as I said, like came a little bit delayed, like in 2000, I think it was 2014 when this denoising CNN was first introduced. I might be wrong, but anyway, it's recent. And these methods are basically defined by three elements. First is the data set they use. So what kind of input and like what kind of noisy image they use and what kind of ground truth they use to train these neural networks. The second differentiating element between these methods is the architecture of the neural network that they use. And finally, the last descriptor is the loss function. So which loss function do these neural networks use in order to train the weights? So from the dataset point of view, this is partially solved. And although like it's not super accurate, that at least we have a somewhat accurate data set in order to approximate the ground truth. As I said before, we do not have actually the ground truth, and we have to invent some ways of collecting that. And in this paper, where you can see the reference in the bottom right hand side, like a method was introduced, which basically just does the multi-frame approach that I just described before. It takes the sequences of the same scene. Of course, the environment is very controlled. The camera is static. It's in the lab environment. The scene is static. And there are some image registration software involved after collecting these images. And then there are many even sub-pixel level registrations to be able to match these pixels perfectly. And then basically then these aligned images are averaged over, and then a ground truth is observed, is collected. So using this data set, there have been 2 image denoising challenges for CNNs in CVPR 2019 and 2020. And those approaches, as I said, like all uses this data set. So we also selected this data set as the basis of our method. Now, coming to the architecture, neural network architecture side of things, common adoptions in these challenge, the neural network-based methods that actually participated into this challenge was an increasingly popular discrete wavelet transform being used in neural networks. So in order to understand why people use this, I just have to briefly mention why we need some sort of downscaling in neural networks in order to have a better quality result. So a receptive field of a neural network is basically defined as the neighborhood that the CNN based its decisions whenever it's making a decision about a particular pixel. So let's say that you apply just one convolution, a 3x3 convolution on the image, and then it means your receptive field is 3x3 because you're using that information, that support area only. So in order to be able to increase your receptive field, you need to introduce many convolutional blocks, which will basically increase your computation. So as a workaround, we can first go to a higher scale by downscaling the image or features, intermediate features later on, and then applying the convolutions there so that your receptive field will automatically increase. However, this downscaling itself introduces some error, especially if you're, for example, doing max pooling or average pooling, which is basically just a mean filter. So there is a loss involved there. So now increasingly people are trying to find some ways to downscale the image in an invertible way. So discrete wavelet transform is one way of doing that. So it's basically, since it's an orthogonal basis, then you basically, if you're using Haar wavelets, for example, then you apply 4 convolutions in non-overlapping blocks. First one is basically just the average of the image. The other ones are vertical and horizontal edges and some diagonal edges as well. Sorry. And one question you might ask, so why discrete wavelet transform and not any other orthogonal basis for this downscaling? And the answer lies in the fact that like discrete wavelet transform also captures a little bit of location information, unlike the discrete Fourier transform, for example, which only captures the frequency information. So this is actually historically also used a lot in classical denoising methods as well. So the common way of using discrete wavelet transform is basically to obtain these downscaled subbands and downscale subbands, and then later on concatenating them in the channel axis, and in the channel axis, yeah, and then applying some convolutions or whatever blocks that you want to apply on those concatenated features. However, later on, in order to go back to the original domain, you have to deconcatenate these subbands and pass it through an inverse discrete wavelet transform. Although it looks like logical in the first look, we notice a potential problem with this because in this convolutions that are applied on concatenated bands, then the order of these bands are not preserved anymore. So this goes against the nature, this goes against the actually motivation of using discrete wavelet transform, being invertible. However, if you cannot guarantee that your band order is preserved, then this actually creates a problem. Although there were although one might say that like CNNs are very powerful structures, it might also learn to recover that band order. We see that it's not the case in the later experiment I'm going to show. So that's why actually we wanted to apply convolutions or any other block on each subband separately in order to make sure that we preserve the band information. And then later on, we go back to the original domain. So in order to verify that this is actually a problem, we have basically selected a very simple task, which is just to recover the original image, the input image by CNNs. Although it looks very trivial problem, I think it was good in order to show that it cannot even solve this simple problem, the common approach. So we just put 10 convolutions in one block here, and then we just wanted to get the input from the output. And as you can see, the common approach is one order of magnitude, performing one order of magnitude lower. This is log scale than our proposed approach. So, and we make sure that the total parameters in both neural networks are same. So basically, the only different factor is the way to apply the discrete wavelet transform. And this was actually the architecture part of our contribution. And as I have previously put, there's also a loss function part. And many neural networks that does image restoration use either L1 loss, like which is mean absolute error, or mean squared error L2 loss, or something like a little bit more complicated stuff like multi-scale structural similarity metric, which was actually proposed to be more perceptually like meaningful, but we also see that it's not. It has been shown that it's not. It doesn't actually correspond to the mean opinion scores later on. One interesting article that I have read, and actually one of the best I have read in this field, I might say, is that for an inverse problem, like everybody was aware of it, but these guys managed to formulate as well. In an inverse problem, that is when there is a loss, there is a certain region that you cannot achieve in terms of performance. So basically, if you lose some information that is not recoverable, you cannot ever go back to the ground truth, right? So, but the crucial factor from this paper was that whenever you hit some boundary that you cannot exceed anymore, you cannot recover perfectly anymore, then you can either go in favor of distortion, or you can go in favor of perception. So this is quite interesting to me, because it says that after some point, if you try to increase the PSNR, you will lose from perceptual quality. So after this paper, actually, people really came up with some loss functions that also covered this aspect to increase perceptual quality as well. And one of them was proposed for image super resolution task. And basically what they said is that, okay, there is a downscaling involved in super resolution. So most of the low frequencies are preserved. So why not only try to recover the mid and high frequencies? And they have shown that it actually helps coming up with a high image quality in terms of perceptual quality. However, this was only limited to a particular problem, and the assumptions were due to that particular problem. We wanted to generalize this loss function, and we came up with some dynamically adaptive loss function, which in each iteration, which focuses only on the frequencies that it failed to recover the most. So first, we take the absolute difference between the discrete cosine transform of the ground truth and our predicted image out of the neural network. And then we select the top K% of the frequencies that we failed to recover the most. And then we only apply our L1 loss on those frequencies. So this helps us to achieve some balanced recovery in all frequencies in the image. So I'm not sure how visible it is over the zoom, but these are some enlarged images that uses our loss function and regular L1 loss function. At least in my screen, it is very obvious that at least in high frequencies, the recovery, like how it looks perceptually is better. However, interestingly, like not so interestingly, PSNR is a little bit bad, but it, as I said, it actually proves a point that that we have hit this boundary, and we have moved a little bit in favor of the perception rather than the actual PSNR. With this method, we have participated in an image. So I will not talk more about this neural network architecture because this is just some regular blocks that people use. We just adapted it to our own method. For example, we adapted this residual dense block so that it can work also in a subband, independent subband order. And the rest is basically not novel enough to mention. So we have participated to a challenge, a Denoising challenge in ICPR 2020, and we came in the 4th place in terms of PSNR. So as I said, like since the PSNR and image quality does not go together, we have only submitted our PSNR-oriented method to that. I have to say that, and it reached to a certain success. That the only difference between our method and the top was like something like 0.1 PSNR. So this, if I were still in academia, for example, this would be the place that I would stop researching this because we have some novelties. We did publish something, and we showed that we are in the world's top denoising method. However, in industry, things just start. So the problem here is actually this: 6.63 seconds per megapixel. And this is inference time and in PC. And we are trying to come up with an algorithm that works real time in mobile phones. So it's a drastic difference. So there were two problems that we are trying to solve. Like, first of all, I put them in the wrong order, but like I'm gonna start with the second one, the speed. So basically, we wanted to have some method that works in under a second for 12 megapixel images that we have in our camera modules in mobile phones. However, the method we have, which we brag about, and the best denoising method on earth, works in 6 seconds per megapixel. So we kind of need, if you also consider the factor of the limitation of mobile GPU compared to PC GPU, we kind of need some ridiculous amount of improvement, like 7,200x in the speed. And the second problem that we faced was the characterization. So this data set was basically collected for a handful of mobile cameras, which are not our cameras, the cameras that AAC produces, and like some common popular cameras like iPhone 7, or I don't remember exactly, but I think Pixel 2. And for do we really have to collect the same data set for every single camera module that we have? And do we really have to train the neural network from scratch for every kind of camera module and every analog gain we have, because the noise model is different? So we needed a clever way to solve these two problems. And in order to solve the first one, we came up with an approach to say, like, okay, let's use the SID ground truth. Never mind the noisy images that they captured, but let's just use the ground truth and consider that this is our ground truth as well. Then but then how to create the noisy images? Like, we had to go to a simulation way. So we couldn't capture, of course, the same scene. And we simulated the noise image from the ground truth by using a little bit more complex noise models than what I just described. And I'm not going to go a lot into detail to that. But the idea was basically to simulate the noise images based on the SID ground truth. And whenever we have a new camera, we characterize it. Since it's our own camera, we know the noise model of that, and then feed that new noise model and create a new data set online. And then we basically just fine tune the pre-trained CNN on other noise models. And by this way, we were able to get very fast new denoising models for each problem we have. So this is how we managed to solve it. And about the speed, like speed optimization and also the memory optimization, because mobile GPUs are drastically smaller in terms of the gigabytes that they can handle compared to PC GPUs. We have used a lot of techniques from the literature, and some of them, as I also talked about before the presentation, were related to neural network compression, which I have some background in Nokia. But yeah, basically, we have combined a lot of techniques, like using more computationally efficient convolutions, like separable convolutions, as done in efficient net or mobile nets compared to regular convolutions. And we have done some model compression. We did quantize the neural network a little whenever we could, in order to be able to make the multiplications faster in the quantized domain. We use knowledge distillation, where there is a teacher neural network and then a student neural network, and student neural network actually is less capable and learns from the teacher and the ground truth in the same time. And we use something called re-representation, which basically, in order to train your neural networks, you came up with some very complicated and memory allocating structures, such as dense nets, for example, or residual nets. Even the skip connection introduces a memory burden. So, however, once you have trained the neural network, you can represent some blocks, getting rid of those skip connections if you design it a little bit better in the beginning. So combining all of these techniques, we managed to go from 6 seconds per megapixel in PC to 4 megapixels per second in mobile phones. And the task is not over. We're still actively working on that. We're trying to fit 12 megapixel, the entire image, under one second. But the progress is pretty good, I would say. So I tried to, I hope I could manage to talk about every aspect of the problem, like the research side, how to improve the existing models, how to apply these improved models to mobile phones. But basically, this is all I have to say about the denoising use case. And for the other solutions that we have in AAC Technologies, we are basically doing similar stuff with the rest of the ISP blocks, like denoising, demosaicing, deblurring, color constancy, etc. And apart from the ISP part, there are also other stuff that we can do with AI in the factory side as well. Like, for example, when you're doing lens manufacturing, there are many stuff that are still under human supervision there. Like, we can automate that project with AI. I don't want to go into much details, but there are tons of projects there. And also there's this image quality aspect, like after applying the ISP, there is a certain number of people, experts, that evaluate how this image actually visually looks. So, which is something that you cannot actually really cover with metrics, because people are looking to specific artifacts, like blocking artifacts or some hazing, etc. So it might be also useful to apply AI somehow in that area too. We also have some projects initiated there. So yeah, this is all I have to talk about. So thank you very much for listening. If you have questions, I would be more than willing to answer them.
Okay, great. Thanks so much, Çağlar. Very, very enlightening talk. Any questions?
Hi, Çağlar. I can ask a few questions. I'm Figen. It was a very nice talk. I enjoyed it. I also work in deep learning approaches in solving inverse problems, not in particular in denoising, but other like image reconstruction problems in general. You mentioned that like the new architecture you described was like the fourth rank in that challenge, like the denoising challenge.
Yeah.
Yeah, I was just like wondering what are other state-of-the-art approaches in denoising, like deep learning based approaches. What are like the architectures there?
Yeah. Mainly like as I said, the difference in I think I have put it somewhere here. Yeah, so basically the difference in the state of the art is basically either the architecture, dataset, or loss function. And in this architecture concept, there is still one thing that we did not do, and I want to talk about it. Thanks for the question. Otherwise, I wouldn't have mentioned it. So consistently, the winners of this challenge are using neural architecture search. So basically, they are also searching for the architecture by another neural network, like a controller neural network. I'm sure maybe you have heard this NAS, neural architecture search, and there are newer versions of that. So since most of the architecture designs, as I said in the beginning of the presentation as well, involves a human element, of course, we cannot come up with the best optimized architecture. But these neural architecture search, there's a great potential there. And as I said, like consistently, the winners do that. And other than that, I think, except for the loss function, there are not really many like crucial differences. Either some people use residual nets, some people use this dense residual nets, use peer ReLU or ReLU as an activation. So it's all I think mess really in terms of the architecture. But yeah, I think like this neural architecture search is a differentiating factor if you want to be the state of the art.
Okay, yeah, that's great. Thanks a lot for the question. Very related question to that about the loss function. Like you described this city type, like new loss function. Was that the one you used in this challenge as well?
In the challenge, we have used regular L1 because the challenge was basically only focused on PSNR. And there were no mean opinion scores, for example. That's why we just used L1.
Okay, and it's like it was also like L1 loss for the other like winners as well, like the best performing ones.
Most of the people used L1, and I think there were a few who used L1 plus MSSIM jointly.
Mm-hmm. That's great. Thanks a lot for the answers.
No problem.
Any other questions? I might have a short question. So in your slide about denoising with the toy trucks, there was this reference 25. The toy truck.
Yeah, I think it was the dataset slide, this one.
So what is this 25? Reference 25.
Okay, so this is actually yeah, taken from directly from the paper. So I really need to go check what 25 is. But I think before the introduction of the smartphone image denoising dataset, people were using some other types of getting the ground truth. As I said, like getting the ground truth to feed to the neural network as desired target was basically the challenge in these neural networks before the introduction of this dataset. And I think this article 25 is just another way of approximating the ground truth, but I have to admit that I don't know on the top of my head right now.
That's fine. So basically it seems like your own ground truth looks better than theirs, essentially. The fourth picture is yours. No?
Yeah, like as I said, like this image is taken from
the whole image. I'm sorry. I'm
yeah,
sorry.
the whole image.
I
Yeah,
see.
sorry about
All
that.
right.
Like
No
I should have made it more clear.
I see. All right. I have no other. I mean, this area is completely new to me, so I have no other questions. Anybody else who has better questions?
I can ask another one actually, but I don't wanna, if there is someone else.
Oh, no, please go ahead.
Okay, I was also curious about, you mentioned like the student network, teacher network, when you were like kind of like skipping through one another approach. I haven't, I think, heard of those network.
Yeah,
I didn't understand how like those things work. I think I'm not aware of it.
It's called knowledge distillation. It's actually a paper by, I'm sure you know, Jeff Hinton, one of the fathers of deep learning. And in that paper, actually, it was proposed for image classification, but now increasingly people are using it for anything else. So mainly the basic idea is that there's a teacher neural network which is more capable, which is over-parameterized, and which performs better compared to when you train a smaller neural network. However, if you train a smaller neural network, not only on the ground truth, but also on the decisions of the teacher network, it has been observed that it actually performs much better. So instead of feeding the classification, like hard classification result of the actual ground truth, if you try to learn what teacher predicted, then your final performance is also better. This is one of the fields that is highly debated in deep learning, and it is still not perfectly understood why this happens, actually. But the paper is Knowledge Distillation by Jeff Hinton.
Okay, thanks a lot.
Okay, so Kerem Aydın has a question that he typed in the chat.
Oh, I haven't seen it.
Kerem, are you here? Do you want to ask your question, or shall we just read from here? Can you see Çağlar?
Yeah, I think we have covered this, but let me reread it again. In the beginning of the presentation, you mentioned automation of architecture selection. You told the selection is still half automated. Is there another neural network that designs the neural architecture? How does it work? Yeah, so what I meant by half automated was referring to basically automating the feature detection and represent like descriptors. However, human element still is there when it comes to designing the neural network, where to wire it, where and how. And the full automation actually still is not there, because basically what this neural architecture search we just talked about does is that it gets some basic building blocks, which is like, let's say, convolution Bayes-Schumann ReLU as a building block, and then searches over all the like number of filters which to apply on top of where to have skip connections. Of course, a little bit better than a brute force search. I think I don't know exactly how, but I think there should be a controller neural network which also learns which way to go in this optimization in the neural architecture search. But yeah, I think like that covers this question. Or if there are more questions, I might try to answer about this.
Okay, cool. Anybody? Would anybody like to say anything else?
I also have one question. I'm not also a specialist in this area. I'm just interested. Big companies also are trying to optimize their hardware for this kind of tasks. Companies, especially like Google, trying to. Is this field is going to be limited to the very like flagship smartphone, or how we expect this technology evolve in this smartphone?
Yeah, I think excellent question. Like currently, I think as in everything else, there's an Apple and there is the rest. And also, I think Huawei is designing its own chip. But other than that, like most people actually rely on Snapdragon, which is designed by Qualcomm. And like as long as we have Snapdragon, I think the rest of the earth will be fine other than Apple. But I think Apple's chip is currently the best on the industry. But the development there is huge. Like in between Snapdragon 888 and the previous one, I think there is like something like 2x improvement in float point 32 number of flops that the GPU is able to do. So I think that field is also developing quite fast. I don't know if it accords to Moore's law, but yeah, it does.
So this kind of technology should be available in this flagship smartphone, not in the mid-range. And so it's really dependent on the computational resource. Am I right?
Yeah, that's totally true. Although, like it's a little bit futuristic, but there are already some works in doing this cloud ISP. Now that there is a 5G, like you can, of course, if you want to upload your image, you can upload your image. I don't know how fast it will be. It's still 12 megapixel image, and then it can be processed in the cloud and sent back to your mobile phone. It's a little bit futuristic, but I know people already started these kind of projects.
Also, Google is very famous for using this computational image processing to make their image look better in their smartphone. Is they're using this kind of techniques, or it's completely different?
So I couldn't understand well. What is famous?
Google is very famous for using this computational type to make their image looks better, and even though they don't have this best camera, but
you mean
people
Google?
say that they are using these techniques to make their image looks even better in the Pixel smartphones.
Okay. You mean Google? Okay. Yeah. Okay, I need to check if Google has its own chip or not, because as far as I remember, last time they were using Samsung Mali GPU, not their own chip, but maybe they switched to their as well.
Yeah, I know they are working on it, but in the current smartphones, is they using this some kind of this deep learning techniques to make their image?
Yeah, not as far as I know. Okay. Maybe Apple, but everything is hidden there, so we don't have access. Like, but for example, this year there was also a challenge we couldn't attend, and it was only based on denoising in mobile phones. So there is still some research from the community. I still haven't reviewed that paper yet, but I think in the next generation of phones, maybe next year or so, I'm sure that we will see some sort of AI applied on these problems.
Okay. Thank you.
Thank you very much.
All right. So if there are no other questions, we will thank Çağlar again for visiting us today.
Thank you very much.
Very nice, very illuminating talk. We would be very happy to have you again in later years. I wish you personally the best of luck with your work. Okay.